this section, we will examine the classification of rocks, the rock cycle, the evidence for plate tectonics, and the plate tectonics movement and how it's classified. In this rock cycle, there are three classifications of rocks: igneous, sedimentary, and metamorphic. Igneous rock is formed when liquid magma coming up out of the volcanoes cools into a solid. This rock creates new mountains. Once these mountains cool, the external heat drives the climate changes that cause weathering and erosion. That begins the breaking down and tearing down of the mountains. Wind, water, and ice break down the rock of the mountains and then move it away, eventually moving it towards and into the oceans. These particles are deposited in layers as sediment that over time turn into sedimentary rock. Finally, these sedimentary rocks get pushed down into deeper levels and under high pressure and high temperature are changed into metamorphic rock. Eventually, metamorphic rocks are pushed even deeper until they are melted and turned into magma, and the cycle starts again. Earlier I talked about the tectonic plates in the lithosphere. These plates have been identified and plotted on this map. This is the African plate. As you can see, it extends far out into the Atlantic Ocean. It is bigger than just the landmass of the continent. We are sitting on the Arabian plate. In the early days, before the plate tectonic theory was proposed by Dr. Wenger, geologists were busy mapping the locations of volcanoes and earthquakes. Over time, there developed a pattern that generally traced the plate boundaries of today. Also, they began to collect other data that proposed that all of the continents might have been one at one time. 250 million years ago, geologists believed the continents were together as one. The 5 major pieces of evidence to support this theory are as follows. First, the present-day continents seem to fit together if you trace their movement backwards in time. South America fits into Africa, and North America fits into Europe. Second, many of the mountain ranges on different continents have the same types of rocks. A good example is the Appalachian Mountains in North America are very similar to the Ural Mountains in Europe. This indicates that they were formed before the breakup of the supercontinent. Third, there are 300 and 400 million year old fossils that have been discovered. When these animals and plants died, they were captured in the layers of sediment and in time turned into rock. For example, when we examine these rocks closely, we see many of the same fossils in South America and South Africa, signifying that at one time they must have been together before the continental drift began. Next, there is also subsurface evidence that sections of different continents show exactly the same ancient climates in the rock records. Hundreds of millions of years ago, places that were hot or dry or wet are exactly the same. Again, where the landmass would have been joined before the drift began. And the 5th piece of evidence is one seen on the ocean floor in magnetic stripes. In this animation, you can see what geologists think is going on. It has been observed that on the bottom of the ocean there are stripes whose magnetic field alternate between north and south. In the center here, this volcanic activity is spewing hot lava that flows outward, filling in gaps as the continents drift apart, usually at the margins of the plates. This lava is full of iron. As the iron ions cool down, the atoms align themselves with the Earth's magnetic field, with all ions pointing in the same direction. Now, for some reason, as scientists still don't know why, every 600,000 years or so, the Earth's magnetic field changes direction, from north to south or from south to north. On the bottom of the ocean, you can observe these stripes. You can measure how these lava flows over time changed magnetic direction. One strip will be magnetized in one direction and the next in opposite direction, creating stripes. You can create the same event in a laboratory by making a magnet. Take a piece of iron and heat it until it is very hot and molten, red hot, almost liquid. As it starts to cool down, put a magnet next to it. The iron molecule is a polar molecule. It has a plus side and a minus side, so that all the minus ends and the plus ends of each molecule start lining up according to the magnetic field. All of these molecules will line up in a certain direction because they are hot and they are still liquid. They can move and eventually they turn into a solid and their ions become fixed in position, fixed in the same direction and can't change. They stay that way and become a magnet. You can do the same with hot rock that is full of iron. They found that rock will become magnetic as it cools. It will have a direction. Like I said earlier, the magnetic field changes about every 600,000 years or so. If you take a compass, one stripe will cause the needle to move north, and in the next stripe, the needle will reverse itself and point south. We don't know why the magnetic field keeps changing, but we still use our powers of observation to describe and record. Now let's talk about the Earth's surface, its crust. We will look at how the crust is ever changing, how it is dynamic. We will describe the theory of how new crust is made and old crust is destroyed. We have identified three types of plate movement at the margins, which is another word for edge or boundary. The three types of plate movements are divergent, convergent, and transform. The first type of plate movement is divergent. In this animation, you can see how the two plates are moving apart. They are moving in opposite directions. In this movement, ridges are created by volcanic activity that spews from the gaps when these plates move apart, creating rifts or holes. It is here where new crust is created. The second type of plate movement is called convergent. In this plate movement, the two plates collide. They push together until the side with the higher density is pushed down and under, and the lighter side is pushed up. The plate that moves up becomes mountain forming, and the plate that moves down continues on down until metamorphic rock is formed, and then, if pushed even further down, it is transformed into hot magma. It is here where the crust is destroyed. The third type of plate movement is called transform. In this movement, the two plates merely move from side to side, sideways in a lateral movement. This movement neither creates or destroys crust. This movement moves the plates back and forth, causing violent earthquakes. Now, let's look at some specific geological examples. On this map, we see symbols that the geologists use to show plate boundary movement. They are divergent, convergent, and transform. Using these symbols to read the map, we can see that the Arabian plate, located between Africa and the Eurasian plate, is moving away from Africa and toward Asia. As the Arabian plate moves away from Africa, this rift, the Red Sea, has been formed. This is divergent movement. New crust is formed when these two plates are moving apart. We also have the Rift Valley. The East African Rift Valley has lots of long, thin places with volcanic activity. Slowly moving apart, it will eventually form an African Sea here, and a new plate will begin to form here. Where the Arabian plate is moving into the Eurasian plate, we have convergent movement. As the Arabian plate moves into and under the Eurasian plate, the plate is slowly moving under Iran, producing the Zagros Mountains, which are being built as the Eurasian plate is lifted. The Arabian plate slips under the Asian plate and old crust will be destroyed, creating a trench. One thing to note, oceanic plates, because of their denser composition of iron, are pushed down. light continental crust made of silicates is pushed up. In all cases, the denser plate, whether oceanic crust against continental crust or continental crust against continental crust, is pushed down. Remember, in divergent, the plate boundaries are moving apart. In convergent, they are moving together, pushing into each other. In transform, the plates slide past each other in a sideways movement. Here is another example of convergent plate movement. One plate pushing against another. The Indian continent is moving. It is a separate plate. The Indian plate is slowly being pushed down under the Eurasian plate. Indian crust is being destroyed, while the Eurasian crust is being lifted, creating the Himalayan mountains. The Indian plate movement is a good example of subduction. In a subduction zone, the area where the plate that is being pushed down, there is a lot of friction as the rock slides against other rocks. It gets so hot it starts to melt, forming metamorphic rock. Then, as it is pushed deeper down, metamorphic rock is destroyed and melted and changed into magma. Some of this magma flows out of volcanoes, creating new mountains. In the subduction zone, we also see a trench forming here and mountains being created here. Mountain building and crust destruction happen at convergent plate boundaries. The plate that is pushed down then starts to fuel volcanic activity, using the crust from subduction that eventually turns to magma that will be used to build new mountains. This is part of a cycle that geologists call the rock cycle. Here is an example of transform margins. The Arabian plate is moving this way. See the arrows? They tell you that the boundaries are moving in the opposite direction. The Gulf of Aqaba was formed by transform plate movement. It goes up through Lebanon and into Turkey. You can see these valleys. It is an earthquake zone. To review, there are three types of plate movement at plate margins or boundaries. Divergent, which causes the plates to move in the opposite direction. This creates holes in the crust that is filled in by volcanic activity, creating new crust. Convergent, which pushes the two plate margins together, causing one side to be lifted, making mountains, and the others to be pushed down into the subduction zone that destroys crust. Transform causes the plate margins to move sideways. This is where you get violent earthquakes, but crust is neither created nor destroyed.